them. If we get a lot of questions, we may have to hold them till the end of the session. Just to test that your functions are working right now and to get you used to the controls, we have a quick function test here. Can everybody see the presentation and hear it clearly? If you can, go to the participant menu and click yes or no. If you answer no, we'll have one of our EC representatives, probably your co-host, to reach out to you and try and correct the problem. I'll just wait for a few moments while we receive those.
All looks good, Rick.
Okay, that's wonderful. So those of you that are attending this webinar, if you like it, please check out our website at energysafetycanada.com/events and you'll see more. As you see right now, we have one coming up on November 10th for Fair Practices Office and one on November 18th for Workplace Stretching and Injury Prevention Strategies. After this webinar, a survey link will be forwarded to each of you at the end of the presentation, and we'd appreciate it if you could complete it, as it will assist us in making these sessions better for the future. With that, I will introduce Mr. Stefan Dobronsky, who's offering our session today, and it's with great pleasure to introduce Stefan.
Well, thank you very much, Rick.
I'll just do your bio here, Stefan, if you don't mind.
Oh yeah.
All the important stuff about Stefan. So Stefan Dobronsky has worked nationally and internationally in various resource industries in various safety positions, ranging from frontline first responders to senior corporate EHS roles and an industrial hygiene leader. He has nearly 3 decades of experience in identifying, assessing, planning for, and executing confined space work. Stefan holds a CRSP and is a member of the American Industrial Hygiene Association. With that, I will stop my sharing and allow Stefan to continue.
Thank you very much. Hello, everybody, and thank you very much for the opportunity to present this. And Rick for the introduction. It's always a bit awkward. Realize I've been at this nearly 30 years. Okay, so we're going to talk about confined space ventilation, and presentation is intended to provide a basic understanding of confined space ventilation.
Are you sharing your screen yet, Stefan?
Oh, there we go. There, can you see it?
Yes, I can.
Perfect, thank you. So the intent is for a basic understanding of confined space ventilation. Fundamentally, this whole conversation is about understanding the risk, hazards, consequence, exposure frequency, and the likelihood of ventilation failures. Let's see if I can, there we go. I've included my contact information outside of this lecture or the conversation. If anybody wants to give me a ring for anything, I see I have a misspell in Hotmail. I'm more than happy to have a conversation with any colleagues. There's a ton of good resource information that I've got squirreled away in various formats. So don't feel afraid to give me a ring, and I'd be able to either give you an answer or point you in the direction who can. All right. So I'm going to make a few basic assumptions during this presentation. That we all understand the definitions of confined space hazard ratings. Confined space program elements are understood, the roles of the parties involved in confined space planning and execution, the employer, the supervisor, instructor, so on and so forth are all understood. I'm going to assume that the isolation requirements are understood, work permits and work records management, along with that hazard is a condition that may cause loss. Risk is the probability that loss will occur, and that exposure control plan requirements is also understood. These are fundamental to defining what type of ventilation planning needs to take place. If folks don't have these fundamental understandings, again, give me a call afterwards and I will be happy to go through each one of those. They are, the terms are very specific and are outlined within regulatory requirements in both of BC and Alberta, and within the industrial hygiene practices as a rule. So the next thing is, let's talk about some of the statistics and why this is so important. 15% of confined space. So these are all mortalities. 15% of confined space training, 15% of people who had mortalities or suffered mortalities had training. 31% of the events had written confined space procedures. None of them had a rescue plan. None of them had a written procedure. None of the events had spaces that were tested prior to entry. None of them were ventilated. And 60% of confined space fatalities are would-be rescuers. So there's a couple of reasons why I pulled these stats out. And just in case anybody's interested, these stats came out of a study that was done out of Quebec that spanned 25 years. And at the end of the presentation, I've got a link to that if anybody wants to go read it. If you're a safety geek that really is a keen interest in this stuff, I strongly recommend that white paper, because it was instrumental in changing fundamentally how a lot of the regulators approach confined space education and requirements. It came out about 3 or 4 years ago. So when we look at these, there's a couple of things that stand out right away. Understanding that ventilation planning is part of the written procedures. So if you don't have written procedures and you don't, or if you don't have them, you've got a big problem. If you have them and you don't use them, you have a larger problem. Now, the reason I included the confined space fatalities or would-be rescuers, which accounts for 60% of the mortalities, is that rescuers are typically highly trained individuals. This is people from fire departments that this is what they do all day long. These are people who are professional first responders from the industrial world that have a, more than just a 2-week or the 2-day rescue training course. And it does include those people who only have the 1 or 2-day rescue training course. The point being is that in every confined space rescue course that you will ever take, of any quality at least, like, a tremendous amount of focus is placed on testing the atmosphere and having a plan, as brief as it may be in an emergency, but having a plan to go in. This is testament to why it's so important to have a ventilation plan along with the confined as a part of your confined space procedures, is because you want to avoid the urgent event where you're not taking, your time is not taken to do those plans, where they're not testing and so on and so forth. We avoid this whole requirement for rescue. 60% of these people would be with us today. Right? So those are some ugly statistics. So hazards and hazard risks and triggers. So these are suggestions. These are my best recommendations. They are not the only way to do this. Hazard examples, so a list of fixed hazards should be in your confined space inventory. So your confined space inventory is not just a list of, I have vessel 1, 2, 3 in building 1, or building A rather, you have vessel 2, 3, 4 in building B, so on and so forth. And these are all listed as confined spaces or assessed as not as confined spaces. It can also include all the fixed components. This vessel has a weir inside it. It is a nitrogen entry. It needs scaffolding to reach the platform. In WorkSafe BC, they have a very good template that I urge everybody to take a look at and either adopt or modify for their particular needs. If you put your fixed hazards in your inventory, you never have to go back and visit them unless you do a physical change to the program or to the space rather. That's going to reduce reduce the amount of effort it takes to do your assessments, and it also is going to centralize your primary information that you need for doing your ventilation planning. We'll come back to what that is in a little bit. So then you've got your dynamic hazards. Those are going to be on your hazard assessment. So your dynamic hazards are things that change once your confined space is being prepared or is prepared for entry, and based on the work that's happening within that space. So as an example, a dynamic hazard is going to be, you've opened the space, you've washed it out, it's been proven to have a good atmosphere, and now you're going to go in and apply an isocyanate-based coating to the interior. You've now taken a safe space and made a very hazardous space based on the potential exposure to a cyanide-based gas. These are going to change as you do work. Welding introduces a hazard. Coating, installation, and removal introduces a hazard. fundamental changes within the mechanics of the interior space of removing mixers or putting mixers in, or changing mixers, installing electrical devices and motors and such. All of those are things that are changing within the space. That needs to go into the hazard assessment. And those will impact the ventilation requirements. And again, we'll come back to that a little bit. Your procedures provide the risk control instructions. So we have our hazards. We have a mixer with an electric motor that's being installed inside of that. The risk is electrocution or automatic starting of the mixers while installation or after installation while other work is occurring within the space. The control is going to be, we're going to physically disconnect the wiring at the panel and validate that that device has zero chance of being activated while work is ongoing within that space. So that part of the procedure, that's one line in your procedure. How are you going to keep this place safe? Okay. I don't recommend combining the hazard assessment and the procedures. And the reason for that's very, very simple. Your hazard assessment is your pre-planning document of all the things you need to do once you're inside that environment. If you combine the two, they can be mixed up. So your hazard assessment is going to include things like what's typically in that space. So you're going to run malt liquor through this open top valve. And the hazard is that you may have free-flowing liquid into the space while work's ongoing. The control is going to be, we're going to isolate, we're going to clean out the space, we're going to clean, remote clean the area before entry. And before even that, we're going to isolate this device by physically removing spool pipes and then deadheading the pipe on both ends. If you start adding what's in place and how are you preparing things to your actual controls of work while it's ongoing, you end up with a very large document. I have seen what some people call as a confined space hazard assessment up to 2 inches thick of reams and reams and reams of paper that includes all the SDSs of the original equipment, includes all the remote entry or the remote cleaning processes and historical information and all kinds of stuff. At the end of the day, the question as professionals that we have to ask ourselves is, what is the guy on the front line going to look at? And if it's anything more than about 3 pages, you have utterly failed to achieve the goal, which is give them a simple, clear, concise document that they can use to validate that the space is safe to enter, the work is going to be performed in a controlled manner, and if something goes horribly wrong, how are they going to get out and exit that space with the minimum amount of harm or injury potential? If you've got anything more than that in your document, you're padding it. It's all important information to go into a confined space package, which I'm not going to talk about today, but that's not what we're looking at. We're just looking at the procedure here. That's it. So the other thing is that exposure control plans are triggered at 50% of any threshold, 50% of the threshold of any contaminant. So I'll pick numbers out of the air depending on if you're federally regulated or provincially regulated or whether you're in BC or Alberta or Saskatchewan. Hydrogen sulfide has has a threshold of 10 part per million for an 8-hour exposure. Now we always want to go with the ALAR principle, which is the lowest achievable rate. Now, if we understand that 50% of our action threshold is 5 parts per million for an 8-hour shift, we need a plan after that. It's a legally required device. It's well understood in the AIHA and ACGIH guidance documents, of which are both referenced by WorkSafe BC and Alberta, along with the federal labor Part 2 labor code. So understanding that if there's a potential that we're going to reach that exposure limit, we need to ensure an exposure control plan is in place as part of this. The reason I mention this is because that exposure control plan is going to give you a lot of critical data that you are going to need in order to do the ventilation plan. What is it we're dealing with? What are the concentrations probably that we're going to be encountering? Is it reactive with other chemicals or other materials? Is it heavier or lighter than air? What's the toxicity? What are the controls that are going to be put in place for people to work in and around those particular products? Pardon me. So in your ventilation plan, when we get to that, the ventilation plan is quite simple of what it needs. You have to have an evaluation of what to control. This is going to include your suspected contaminants, your measurement methods, your thermal differences, and that's one a lot of people forget, because even though something might be lighter or heavier than air, if you've got convection currents going on within that space caused by thermal considerations, you are going to have to take that into account when you're doing your ventilation planning and your measurement. So after you've got your evaluation, you have your flow rate. So how much control to apply? So we're talking specifically in this case, how much air are we moving through the space or into the space? And then finally is the method. How are we going to control that? Are we pushing air? Are we pulling air? Are we using natural ventilation or mechanical ventilation? Where are those mechanical air movers connected or located? This is fundamentally what a ventilation plan has. And that's really all it is that we need to be concerned with. So under evaluation, space configurations are going to make all the difference. That's going to include everything from an excavation, and yes, a ditch or excavation can absolutely be confined space. Look up the definitions in your regulatory area. Long story short, if you have an excavation that is more than, I think it's 4 feet deep in BC, and your slope on your walls is greater than 45 degrees, you start asking questions right away, because if you're going to introduce any form of a toxin, you are more than likely going to be in a position of that excavation is now being considered as a confined space. There's a bunch of other criteria, but there's some mathematics we're going to talk about later about why the space configuration specifically for excavation is a bit tricky. Obviously, the next big bucket is going to be is it an enclosure? Do you have trays, or calling multiple flow restrictions? Do you have ventilation levers that might be auto actuated, or you need to position open or close so you can direct your air movement? You have single or multiple flanges or ports to push or pull ventilation through. You have multiple connected sections. So there are, out in multiple industries, we have a vessel or a space that's connected through piping or an adjoining structure, and then another space. We can't always get blinding into those, or we can't get isolation into those. So when we run into those space configurations that are a bit unusual, we have to we have to do the calculations for that entire space and consider how are we going to do the ventilation depending on the work that's going on in the entire area for that. These are all things that are going to impact your decisions because of opportunities that are going to exist based on that space configuration. The other thing is, initial entry conditions. Is your initial entry going to be a dirty entry? So if you're opening a water cistern, you're going to expect there to be a little slime or sludge, but it's not going to be expected as a toxic environment. We're going to measure it, we're going to monitor it, but it's not expected. If you're going to go into a space that's been holding asphaltenes and it's full of stuff, and you haven't been able to do a zero entry washing, you're actually going in. That's going to make a big difference on your ventilation planning. Is the air you're going to draw out or push through going to be problematic? How do you manage that? Is it going to go through a scrubber? Is it going to atmosphere? Are you going to, cordon off an area and use natural dilution? Are you, by opening the space and putting oxygen into there, are you causing secondary problems with pyrophorics, things like that? So these are all, thoughts when we're starting to do our ventilation planning, is what does this all look like?
Now, Stefan, you indicated that your plan shouldn't be any more than 3 pages. You're not talking about a confined space plan, right? You're just talking about the ventilation plan. Is that correct?
Talking about the ventilation plan.
Thank you.
Yeah, good question. Excellent question. So remember, when you're doing your initial entries, when you're doing your initial readings, you have to turn your ventilation off for 20 minutes before your readings are taken. If you've got your ventilation on and you're taking your readings, your initial entry readings, you're not providing a true sample of the air that's expected to be in that space if your controls failed. Again, part of your planning is, do you need a large amount of air or a small amount of air? But you can't demonstrate that without doing some tests in a stagnant environment. Okay. Shall workers be entering a clean space or doing, are they going to take contaminants in with them, so on and so forth? Residue last contained is another big issue. So if you've got a clean space or relatively clean space, did you introduce a inert gas as an example, nitrogen, so on and so forth? Will there be chemicals released with different working conditions? Are you going to use a torch in there and heat up the material? Is it going to off gas something? Will ventilation introduction cause problems? So I talked about that briefly a minute ago here. Iron sulfides in the oil and gas industry is a very good example where residue last contained. We ran water through it. We did an acid wash. Then we nitrogen purged and we oxygen purged. We opened the doors, and lo and behold, there's this wonderful brown stuff on the inside of the vessel, and we throw an air mover in there to, get our 5 or 20 air exchanges, depending what we need to do before our initial entry, and suddenly the thing's on fire inside. And what's happened is the residue last contained wasn't considered that it may have iron sulfides in this particular example. There's a lot of chemicals that can do that. This is just the most prolific one in the oil and gas industry that I'm aware of. The other consideration is what's the chemical relation to the mass of air. Is it heavier or lighter than air? So that's molecular weight or the mole weight. It's air density is another measurement we can use to explain that. So if you're opening the door and your residue last contained is butane, which is going to be lighter than air, you may have a space that's got the first few feet is good, and above that you've got a problem. And likewise, if you've got something that's a heavier than air component, it's going to sit in the bottom of the vessel. If you're climbing down into that, that's problematic. We'll kind of talk a little bit more about that in a live example later on. But those are all things we need to keep really aware of with the residue last contained. Another thing is the original, with the residue last contained is, are the contaminants going to react with cleaning agents or with other products? So I'll use the example of a product called Morphosorb. It's used as a sulfur scrubber. It's a very, very good product. Works using heat or using pressure differential. Problem is when you open the doors and you introduce nitrogen, not oxygen, it turns into morpholine. Morpholine itself is an incredibly toxic, carcinogenic, corrosive chemical. What was in there a minute ago was fine, but not understanding the residue last contained created a problem the moment you opened the door. So isolation is another one. This is common in confined spaces, but when the ventilation planning relationship is, do you need to have all those doors open or closed? How are you going to make your ventilation planning? Are you going to draw or push from a single place? And how you measure your effectiveness, and I'll show you that later, is going to make a big difference based on the isolation philosophies of that vessel. Fundamentally, you don't want to get any toxins in or contaminants in, and you want to manage what you're pulling out of that environment in a safe way. There's lots of ways to do these things, but when we're talking with the planning folks it's not just the stopping of the liquids or the gases from getting into the space from the other process units. It's also what do we need to do as the people planning the ventilation. This is probably the biggest missed opportunity in the majority of confined space planning that I'm aware of. So will ventilation introduce contaminants to measure to another area? So if you are buffing out a coating, an epoxy coating that's high in titanium oxide, and the guys inside there are doing really well, they're using supplied air because they can't reach an appropriate safety factor with a full face or half mask. They are fully aware of the toxicity of titanium oxide dust in the lungs. They've got a decontamination unit. Everything else is taken care of. but you're blowing that stuff out the top of that vessel and it's raining down on top of everybody. And it has an extremely low threshold of acceptability. So it's, your parts per billion. You've contaminated not only the area, but you've now introduced a toxin to anybody walking by there. So when we're starting to look at ventilation contaminant management, there are all kinds of components around that, along with not just what are we doing, but how are we measuring that, or where are we measuring that? What are we measuring for? And so if you're measuring for contaminants inside the space at the bottom, when you're blowing the contaminants out the top, you're going to think you got clean air, or you're going to demonstrate through your measurements you've got clean air at the bottom, which is incorrect. You go up top or you go outside that area, you're suddenly going to realize you've got a significant issue that's been caused by not properly managing that. And it's not just how you manage the product, but where you take the measurements. The reason I mention this in such detail is when you're doing your ventilation planning in the procedure, you need to be very clear about what are they measuring for, how are they measuring it, where are they measuring it, what is the occurring events while they're measuring it, and the tasks inside the space, so that if anybody ever has to come back and ask the question, we are able to demonstrate with very clear instructions why this was the right thing to do. Okay. So we talked a little bit about heat causing a difference. So if you're running a really cold day and you're doing a pressure hot sea wash or a heated wash inside a vessel, those gases that would be near neutral or slightly heavier than air are suddenly going to be carried out the top of that vessel if you're venting through the thermal waves. And this is really, really important to understand, because it goes the other way as well. We can draw air in if it's cold when we're doing cryogenic processes and systems. Just be aware of these things as to how are you going to manage it. We're going to show you some stuff later on with some basic diagrams as to how to manage those things. All right. And will additional ventilation or evaluations be needed as the space changes? So we talked about the example earlier where we've cleaned the space. It looks really good. We've done all the work, and we're going to start introducing your isocyanate-based internal coatings. Well, all your gas monitoring goes out the window the moment we do that. And again, we have to be very cognizant of each stages. During the cleaning, we release hydrogen sulfide, asphaltenes, and benzenes. During the inspection, it was good. There was no new introductions, so that space is going to be fine. They may have gone in and done some mechanical alterations that didn't make any changes to the atmosphere in that space. We just continue on with the standard atmosphere ventilation. But the moment we start introducing new hazards, whether that's a coating or off-gassing of materials, everything has to change. You have to be prepared for that in your procedures. So in ventilation methods, there's fundamentally 4 basic considerations: natural ventilation and mechanical ventilation. Natural ventilation is the most desirable and the least used, primarily because people don't take the measurements and understand what needs to be accomplished. We need 50 CFM per worker inside a confined space where we're not introducing a hazard. We have a good atmosphere that exists, and we're not welding, specifically welding. That's not a lot of air. And if, we can generally get that through natural ventilation in many spaces. It has to be measured. You can't take a guess. There's lots of good devices to do that. Mechanical ventilation, number one sin I've seen in the oil and gas industry specifically is people put a gigantic air mover on thinking more air is better, and they blast the air into a space, and they only need, I'll pick a number, they need 2,600 CFM, and they're shoving 10,000 CFM through a space, and they're causing harm and discomfort to the person they're working. I've literally had my hard hat pulled off when I was entering an area to do an evaluation through a 36-inch pipe, and it literally sucked my hard hat off my head and pulled it down through 50 feet of pipe to the other end and pushed it up against the ventilation device. That's a little bit much, right? So measurement is everything. Mechanical ventilation is also very noisy. Most stuff we see in the oil and gas industry is venturi based or air driven. So you've got all kinds of stuff going on there. Again, if you don't have to have this thing blaring away, don't do that. It's not necessary. So general ventilation is you're going to move air through or into a space or pull from a space. Local ventilation is typically a much smaller scale, and it's to remove a specific toxin or hazard, dust, gas, whatever that looks like, but from a very, very localized space. So welding is a good example. We use a lot of local ventilation. It keeps the majority of the smoke and the fumes out of the area so that the risk is minimized. So the other thing is, are we going to push or pull air? And when we're looking at ventilation, again, there is a number of considerations around that. Generally speaking, pushing air into a space is more efficient than pulling air out. Although not always a true statement, it's a general rule of thumb. You get a better dispersal of air through the space. It mixes better. It pushes the air from the back to out through the front. Lots of things that it's generally, again, by the way, there are specifics where you don't want to do that. And if you're generating a toxin at one end and you're trying to keep that toxin away from the rest of the space, or you want to keep the rest of the space having clean air, you're going to take a sock, take it down to that far end and draw the air out of that space. All right. So airflow location. So where are we going to be pulling the air from, pulling it through? Do we have weirs or screens or trays or other devices or walls and so on that are going to direct our airflow? And where are we going to measure that? Right? So airflow direction is critical for managing contaminants, especially that are heavier or lighter than air. If ventilation is to remove or manage temperature, or it's for the management of contaminant direction. Also, the assessor needs to confirm that there are no unplanned contaminants being drawn into the space. Examples of these are going to be, where is your mobile plant? So it's your compressors and light plants and pickup trucks and welders and all this kind of stuff. This is really critical in a highly dynamic workplace. So shutdowns or major construction jobs, you have things changing minute by minute by minute. You can introduce a toxin to a workspace by simply having a truck idle within 25 feet of a high volume pull, or where it's just being carried downwind. So be mindful of not just what's inside the space, but what's outside the space. And again, be clear in your procedures. What are your expectations around that ventilation planning? We talked about air being expelled, and not just how are we doing, but where are we doing it? Top, is it the bottom, is it the sides? Are we putting it through a scrubber? Are we going to put it through another device? All this needs to be extremely detailed in your methodology. Right. So the other one is single or multiple mechanical air movers. So if you have a very large space, we're going to need to start thinking about how do you overcome head pressure and move that air along through. If you have I'll pick a number, if you have a 200,000 barrel tank, one little 500 CFM air mover is not going to do it. You're going to probably need to put, I'll pick a number, 10,000 CFM air movers in a daisy chain, running air in a circle. You're going to want to push air into one location on the bottom or the top and pull it from top and bottom with more air movers. We start getting into very complex processes and systems. The really important key for that is not just on our planning, but how do we validate that that's effective? If we want to start talking fluid mechanics and figuring out how far to space our air movers apart, again, I can talk to you guys about that offline. There are some very good mathematical models to follow, but that's a long conversation that would exceed the 1 hour we have here. Ventilation methods. So this is the last part of this real big one here. So what are the volumes we're looking at? It's going to be dependent upon the concentration of the contaminant that's present. All right, so are we looking at pushing or pulling? We talked about that over and over again. We talked about the requirement for 50 CFM. But when we start looking at something like a welder, you're going to need 2,500 CFM per welder, and that's assuming the space is 10,000 cubic feet. There's all kinds of requirements to start looking at in great detail around fumes and smoke and dusts and stuff like that. Part of the ventilation method we talked about was local ventilations. So here's a chart that I pulled out of AIH booklet that gives us some very basic things for welding. So if we have local ventilations, 4 to 6 inch inlet, it's only going to move 150 CFM to 3-inch duct. And we can go from there. How much area do we have to move? So if we're doing, 1/4-inch rod, which is massive stuff, 600 CFM is probably going to be enough, but 150 will not. It'll overcome the requirements. Okay. So just again, think of the ventilation. Why are we doing the things we're doing? How are we going to get them done? Can it actually be accomplished? Are we just dreaming things up, or, is there a better way? Number one way I figured out to do a lot of the ventilation planning in my career is I sit down with the tradesman and I ask them, how has it been done in the past? And then I put the math to it. So a couple of really important things. There's no way to make math fun. I'm just going to throw it out there right now. We need to understand area math and we need to understand volume math. I'm not going to go into it in detail. I've left these in the presentation so that people have them. I will show you in a moment why they're important. Okay. So as we start going through airflow, the last thing is need to measure it. Putting your thumb in the air or holding the ribbon up is good to confirm that the airflow is existing, but it's not going to give you a scientific measurement of, are we actually moving the right amount of air? Too much, too little, the wrong direction, so on and so forth. A couple of things when we're doing these measurements, make sure that our scale is correct, and whether we're consistently using either a standard or metric. Really, really important, because feet per minute is what we need to end up with. Cubic feet per minute is a standard explanation for velocity and volume. If you're reading in, inches per second, or you're reading in miles per hour, you're going to have to convert those back and forth. Really important to get this. So check your meters always, understand what's going on, and get that sorted out right away. For our flows, we need the velocity times the area of the space in order to calculate that out. Okay. So I just threw on here some conversion tables that are really simple, so that depending on how your device is reading, you can flit it back and forth to feet per minute. Again, that's the most important one there, that second column. Okay. So the other thing to talk about is you can't just stick your anemometer or your wind speed indicator across the port with the face of what you're measuring and say it's good. You really need to get the average of what that face looks like. Now that's going to depend tremendously on how big a space is it. Are we talking a 72-inch sewer opening, or are we talking a 12-inch duct? Generally speaking, minimum for smaller stuff I use is, we're talking 6-inch to probably 12-inch. I use a minimum of 8 points. Something about a third of the way down out from the center, and then a third of the way closer to the edge. But these are some examples of where you need to, when you're doing your measurements, make sure you mark down what was the value for each one. You're going to add them all together, divide by the number of measurements. That's going to give you an average airspeed. You're going to use that average airspeed to calculate flow based on the actual size of the device. So here's a diagram of a simple space, right? You've got some internal weirs, but basically you have one manway and a pipe in and a pipe out. And so for this example, we're going to talk about this being a stainless steel potable water tank. It's been disconnected for inspection. Work is taking place during summer months. It's cylindrical, has a length of 14.3 feet by 60-inch diameter. Inlets and outlet pipes are 12 inches and the manway is 12 inches. These are important components for the mathematics we're going to show you in just a moment. If additional airflow is needed, it should be injected at the lower flange. So convection flow goes out the top. It's going to help, or at least not impede upon the flow. Right? If we change this chemical to bromine gas, it's got a vapor density of 5.1 to air being 1. How's that going to impact the ventilation? Also consider that it's got an LC50 value of 116 parts per million, which is very, very toxic. And with it being 5.5 times heavier than air, the airflow will have to be reversed. You're going to shove air in the top and eject it out the bottom. You've also need to make some different considerations with your ventilation planning. This stuff is very, very toxic. Where is this venting to? How are we going to manage this? Can we use diffusion? Do we have to use an exclusion zone? Do we run it through a scrubber? Do we process it in a different way before we get to this point so we eliminate the bromine entirely with a scavenging agent? All these have to be included in your ventilation planning, right? The other thing is, we talked a little bit about reactivity, is the chemical that you are pushing out of the space reactive. So, if it's reactive, what is it reactive with, and how do we keep that safe? How do we keep the people safe? So let's, we're going to talk about the initial ventilation calculations. You're going to hear me talk about initial ventilation is basically proving the area is safe. So if you're introducing hazard, you have to go back and prove it safe again. But the mathematics, unless you physically change the space, should be same. So again, we're talking about the same stainless steel tank. It's disconnected for inspection. It's during summertime. You've given the dimensions exactly the description I just gave you. First, you're going to figure out the volume. So you're going to convert your diameter of 60 inches to 5 feet. Sorry, I should make that 72 inches. Now you're going to calculate, your 963.1 cubic feet or 27.3 cubic meters. You're going to take the number of exchanges that this product requires. So in BC, there is a minimum of 5 exchanges before you enter a space required. Because this is a non-toxic tank without any expectations of oxygen scavenging or anything else, the 5 is just fine. Right? This will be determined by your safety professional or by an industrial hygienist. If you have questions, I recommend you call your local occupational health and safety board officer. I've never had a problem with them being anything other than excellent resource for information. Third is you're going to figure out your exchange rate. So making the assumption with the understanding the volume and the exchange number of times we have to exchange the contents of the space. I'm going to take the times of the vessel volume by the number of exchanges water divided by 60. And that's going to give us our minimum flow rate. In this case, it's 80.72 CFM. When we put our air flow on there, do we actually have that or not? And so if we've achieved that, if we've got 100 CFM, we know that we're going to be good in 1 hour. That's fine. Now, because this is initial entry, we don't have to do it in 1 hour, but we have to do 5 changes. So if we don't have that, we have to work backwards and figure out how long is this actually going to take. 5 hours, 5 minutes, but we need to have the 5 air exchanges. Don't forget, when you're done, you got to turn it off 20 minutes before you do your initial tests. So once we've done our assumptions and our math on this, we're going to actually go out and measure the actual flow. All right. So to validate your flow, you're going to go out there and you have to understand your pipe flange diameter. In this particular case, we have pipe flanges are going to be, 12 inches. So a 12-inch flange is 0.5 of a foot. So remember, you're not dividing by inches, it's percentages of a foot, right? So it's, you're going to do pi times the radius squared. So for a 1 foot flange, 0.5 times 0.5 times 3.14, that is going to give you 0.25 times 3.14, and that's going to give you 7.785 squared area. So that's going to be important, because depending on the speed of the air going through that hole, then you can work backwards again and calculate what is the actual CFM going through that space. Similar with the manway, you can do the same thing You're going to go, it's a 24-inch manway. Your radius is 1 foot. You go 3.14 times 1 times 1. That's going to give you 3.14 feet squared. You're going to measure the airspeed across the outlets, one pipe and the manway. So we're going to assume 24 feet per minute at this point. And you can see the equation in the bottom. That's where we end up with 94.2 CFM going through that area. So we know that we've well and exceeded the 50 CFM per worker. We are well below a requirement of 2,500 CFM for a welder. But as we start working through all these equations, we can prove with math whether or not we are adequately managing the air movement through this space. Right? Now, this can be very simple, or if you've got multiple spaces and multiple things, it can be very, very complex. Okay. So let's go back to the whole conversation with the bromine. How is this going to change it? Well, the only real changes we're going to see, the math is going to be identical, but the number of initial ventilations is going to change. So we know that 5 air exchanges is going to give you approximately 95% of air exchange in a given space. It's a typical space. There's some fluid mechanic assumptions in there that things aren't really crazy and in weird shapes. That's typically what we're going to see. Well, at the toxicity of 116 ppm being your LC50 value, we don't want to only have 5 exchanges. 5% being left in there is going to plausibly do a lot of harm. So we're going to up that to 20 ventilations, and then we're going to measure it. We're going to make very, very sure. And 20 might not be enough. You might have to go up. But again, you need to understand what is the products you're dealing with, what is the space you're looking at to figure that out. Okay. So that's a simple space. The mathematics are always going to be the same regardless of anything else. That's one good thing about doing ventilation planning. The math is the math. So when we're starting to look at multiple spaces though, we have to start doing multiple measurements. If you've got a whole pile of egresses, you have to start looking at that. So the one thing that we have to look at right away is it drawing in the top of the bottom? Does that make a difference? Do we need that space isolated, or do we need it interconnected? And you're going to have to crawl up and down in your plan, figure out every place you have to go measure, and then someone's got to crawl up there and take the actual measurements. We can't just check on the outflow and make the assumption that that's good. And I'll show you why in just a minute. You want to pull on where are all the non-powered circulation points, right? So I talked a minute ago about trench. We're about 10 minutes out, folks, just to let you know. Trenches. So is it a confined space or not? If it is, you're going to have to start figuring out what is the airflow potential through that. To calculate that, I've got a formula here that I've left out there for everybody to do. Essentially, what you're looking for is you want to calculate the total volume of space. You want to calculate the cross section. You want to calculate the surface area, and you want to put that into a relationship of your horizontal to vertical ratio. So most ventilation in trenches is natural. There are cases where it's not. Top of the tank may be an example of this, or if you're doing a deep trench, often in city limits where they're doing vertical sidewalls, there's all kinds of stuff in there. Wind flow running across your smallest measurement, which is going to be your cross section, will give you your exchange rate. Usually we're going to see more than enough. Not always, but we're going to use the math to prove it. There is a point at which depth to height relationship starts to be a problem. General rule of thumb is if your depth is 3 times greater, if your width is rather 3 times, anything less than 3 times your depth, you've got a problem. You need to start checking that very carefully. So imagine a 20-foot deep trench with only a 2-foot wide spot at the top. The bottom of that trench is not going to get adequate air movement. You're going to have to do some mechanical ventilation. Versus when you look at the other end of that, you can consider a stadium, which is a gigantic area that's got this similar shape to a trench, your depth to width ratio is 1-to-1 typically. You should be just fine. Again, if you have any doubts, measure it. You got the wind meter, the anemometer. Protect yourself first. Go in and take the measurements. Always confirm. So here's some common problems with ventilation. One on the left, the one I see most often, drives me absolutely bonkers, and most people in the safety industry. If you're going to hang an air mover, let's make it effective, right? You will reduce your effectiveness by up to 50% by doing it the way on the left. More importantly, if you're pushing air in using that methodology, you are going to potentially circulate further toxins or draw things in that were not intended, as far as dust, debris, gases, fumes, smoke, so on and so forth. Don't be lazy. Again, this all comes down to your planning and your ventilation planning documents. How are you going to secure them? You're going to bolt it up on the top of the right-hand picture, or you're going to put it on with a clamp at the bottom. There's 100 other ways to cut this onion. This is just one example of getting those fans or those mechanical ventilations properly mounted. Here's some other examples. Again, using plywood plate adapters or steel plate adapters. The other thing is, if you're going to be potentially working in an explosive or flammable environment, you need to make sure you have an electrical bonding strap. Right? Anytime you've got fluid moving through a space like this, there's a probability of creating static electricity. Again, it's a $3 battery strap from Canadian Tire, prevents a potential problem. Really easy. These are really, really important if you're blowing into an LEO environment, right? Ventilation effectiveness. So you're going to think about this really carefully. How are we going to effectively get the ventilation in? If we're doing the one on the left, the example on the left, we're going to get a nice circular pattern away you go, full ventilation. The one on the right, you get head pressure or chimney effect, where it's just going to shoot down and straight back out, and your sidewalls are not going to get properly vented. That's very problematic. Again, some very fundamental things. Air recirculation, if you're going to short circuit it across the top, you can see the one on the left is problematic. The one on the right is better. Not always correct. Air flowing through multiple spaces we talked about earlier. There's some examples as to ways that it can be done. You don't want to go into where the air is contaminated. You want to go in the fresh air side, obviously. Right. Here's an example of using localized ventilation to pull air out of a space along with the smoke. My immediate question with this is, is this an open-ended tank? I'm going to assume on the left-hand side it would be. I would be comfortable with that. If this is a closed tank, I would actually be asking for some very strong indications as to why there's not additional ventilation going into that space. So primary movement of air is just the basic displacement. That's all fine for a regular environment of just moving air through it. But if we're dealing with other methods, we talked earlier about air displacement in the 2 pictures ago. This is the way I would prefer to see a enclosed tank have local ventilation at the welder and air being pushed in behind the individual or into the space to make sure that they're safe. Quick diagram about heavier than air concentrations. You're going to pull from the bottom and push from the top, obviously, and reverse it for lighter than air. Oh, sorry. Long flow displacement we talked about. There's just an example of a daisy chain ventilation system. These can get very, very complex. Again, if you're not 100% certain, before you put anyone else in there, you protect yourself. You go in and actually take measurements and confirm that that's adequate. Now, one of the ones that I see less often is there are ways to use wind direction to use natural ventilation. Again, we always want to measure, but think about how you're positioning your systems, especially for natural ventilations. Are we trying to capture the wind and force it into an area, or are we trying to use the wind to draw out, using a Venturi effect, draw out the air? And again, it's going to really depend on the space and what are the contaminants. So a couple of quick things here just around references. These are links. WorkSafe BC has got some excellent stuff around their regulations and guidelines, the flow chart for making decisions. Alberta's got some good stuff as well. It's all quite intact. The AIHI Field Guide to Temporary Ventilation of Confined Spaces is probably the best book I can say anyone who is doing confined space ventilation planning, you should have this book in your inventory. It will help you a lot. It provides all the mathematics, examples, along with probably 50 or 60 different scenarios. I've just touched on the most briefest of them. That is, if you're only going to have one book in your arsenal, that's the one I recommend for this particular one. I talked about below the study based out of Quebec. And this is the IRSST, excellent study, fantastic information. There's Confined Space, Health and Safety in Confined Spaces by Neil McManus. It's an older book, still very, very relevant. It's one I've got, I think, on my third copy already. I just wear them out because I constantly refer back to it. Neil McManus is retired, unfortunately, now, but he was the primary advisor to WorkSafe BC for many, many years. Amazing man, excellent book. And then the Health and Safety at Work in Confined Spaces out of the UK. Again, excellent resource information. I've got this one in my bookshelf. I've burned this one up several times.
Thank you very much for that, Stefan. You got a little bit more here?
I got 2 more slides.
Okay.
So the COSH has got 2 online courses. Strongly recommend them for anyone doing this at work. WorkSafe BC has a number of reference manuals. And there's some examples of forms. And that's it. Thank you.
We very much appreciate your willingness to provide some information to the industry here. There's definitely a lot of detailed information that was exchanged there. Thank you very much for your presentation. If there is anybody online that would like to ask any questions of Stefan, now's your chance. We are at an hour at this point, but we're definitely willing to try and field some questions. Here's one. Are we going to get access to the links in the presentation? We will, this presentation is recorded. It will be available on our website as a pre-recorded material. So you'll be able to get them that way. But for those of you that wish, that indicate on the chat, we could probably, with Stefan's approval, we could probably forward the information to you directly.
Absolutely. I'm more than happy to share it.
Can we use our mics to ask a question? That'll have to go to Lucy. Lucy, can you activate Ronald? Yeah.
Hi, Ron. You should be able to unmute yourself, Ron.
Okay, great.
Yep, there you go.
Cool. Hey, Stefan, great presentation. I'm just wondering if you could do me a favor. I'm not sure if it's clear to everybody in the presentation about, we talked about ventilation requirements, but I'm not sure you really touched on when it's required, meaning if you're going to be performing work inside a confined space under supplied air or SCBA, then ventilation requirements really don't factor into it. And it also depends on the work that you're going to be doing there, where you're going to change the atmosphere, which I did hear you say. So can you maybe just elaborate on that? So I want to make sure not everybody on here thinks that every time they go into a confined space that they have to be calculating ventilation, because some of it may be out the window when you're under supplied air.
Okay, so that's a great point, Ron. I'll cautiously answer this because every situation is going to be a bit different. So if you have a toxic environment, do you need to ventilate? My answer is going to be that following the ALERA principle, we want to ventilate to the greatest degree possible unless that ventilation introduces a hazard. So we talked about iron sulfates earlier. That's one case where you don't want to do that. Your ventilation planning at that point is going to be, you still have to plan it out, and you're going to want to make sure you very clearly illustrate what you're not going to do, because it's very irregular not to do that kind of planning. If you're just going in under mask to do you're going to replace a seal in a 15 or 20 part ppm H2S environment, as an example. Like I said, I do encourage everybody to ventilate. You really need to think through, how do you get into this space and keep everybody as safe as possible. Even if you're only reducing the risk and not eliminating it, you still want to work through all of those thoughts. If something goes horribly wrong, you're going to want that documentation. But more importantly, as we talked about at the very beginning of this whole thing, is you want to think through everything very carefully before you start the job, so that we can avoid those circumstances where we have rescuers putting themselves in harm's way.
Yeah, that's great, Sven. I totally agree. I was just going to point out that I think we should all be practicing. If you're not, you should be always thinking about zero tolerance. So in other words, never putting anybody into any type of space that has any type of chemicals of any kind. So you do everything you can, like Stefan said, to clean it out and ventilate it so you know go into a safe space. Where it truly comes into play is when you're going to change the atmosphere, performing work on the inside. So I just wanted to make sure it was clear amongst the individuals participating, because I didn't want people leaving here with the impression that every time they go into a confined space, they have to have all this ventilation set up if they don't require it. But they do truly have to know when they need it and don't need it. Thanks.
Yeah, absolutely. Like I said, the planning is the key point to all this.
Yeah. Okay. Thank you.
Okay. Thank you very much. I hope that answers your question there, Ron. We don't have any other questions per se, Stefan, unless they come in immediately. We thank everybody for participating on your lunch hour. And we hope to see you at future presentations. Thank you very much, Stefan.
You betcha. Bye-bye, everybody.